I'm going to ask if you could introduce your team.
Thank you, Peter. Thank you so much for having us join in today. Rebecca and Terry have been mentioning you as a group for a while now, and we've always tried to kind of connect. And it's awesome to finally do so and share some of the work that we've been doing. I'll introduce the team in a second. Just really briefly to add to my introduction, I'm an architect by training. I'm a professor in the architecture school in Cornell and directing a research lab called the Environmental Systems Lab that really tries to kind of teach architects about sustainable design and most importantly, the computational methods that we can use to design more sustainable buildings. And that's really kind of the research focus. And so today I want to share some of the I'm going to share some of the ideas here that we kind of developed for kind of an urban scale approach to decarbonizing the built environment. And at Cornell, this team that I'm leading or that I'm glad to have beside me is kind of a group of students from all across the campus. So we have systems engineering students, architects, environmental engineering, computer scientists over the last couple of years, really a cross-disciplinary group from all continents and from all kind of subject areas, and it's really exciting. So two of this team are here who have been kind of really leading the energy modeling work in Ithaca and Tompkins County, and also some of the cost analysis. And that's Hongming Zheng, who recently graduated, as well as Cheng Li, who is a new PhD student in the lab and will be kind of, I think, taking on the lead of this project moving forward. So this kind of cross-disciplinary work that we're doing, and in particular this digital twinning work, is of course the work of several years in a team that's a little bit bigger, and I'll kind of highlight who the contributions individually kind of as I kind of show some of the research work that we've been doing. Now, what unites us as a group, I think, is this urge to help society to decarbonize the built environment, as already it has been said that buildings or the architect's responsibility, let's say, to creating sustainable architecture is really significant. So almost 30% of global greenhouse gas emissions are really just due to building operation. So that's heating, cooling, lighting, running electric appliances, and so forth. Construction also plays a role. And we in the lab kind of want to include the transportation part as a significant factor here as well, that we want to take some ownership at least over that as well, or responsibility, because the way we are designing cities obviously has an impact on how we're moving about in cities. And so kind of we're very interested in kind of creating more walkable, more bikeable neighborhoods as well. Now, looking ahead, so the UN predicts about a doubling of the floor area as we move towards 2060. We have urbanization trends. We have kind of cities built from scratch, more in the global south, and kind of urban growth rates that are mind-boggling in a way. And so it's a kind of double-edged sword in the sense that we say, well, as architects, we were happy. There's lots of work for us down the road, but of course, it's a huge responsibility to do this right. And I want to be less pessimistic about this and say this is the opportunity to kind of decarbonize our built environment, create sustainable and livable kind of urban areas for humanity. That's kind of the big goal. And so when the City of Ithaca started with the Green New Deal, the back then sustainability director kind of reached out to us, and we were really excited to see, okay, like how can we use some of the things that we've been developing for design firms, like software tools that we've been developing for architecture firms and maybe urban design firms, how could we leverage some of these to support the city's kind of Green New Deal? And it's a kind of multi-objective approach that we are really interested in. We are interested in transportation, even though this conversation today doesn't really focus much on it. And then, of course, there is the energy supply side that can be talked about. And then there's, of course, the buildings that all we can think about retrofitting buildings. We can think about how do we adaptively reuse kind of existing structures to kind of meet the city's demand and so forth. And of course, life cycle and material use is also a question. So we kind of started to kind of with this idea of how can we create like a digital replica of the city, and by what we mean by that really is like, let's gather all the information that we can get about buildings, and then let's try to make turn that into analytical models that we can then test for accuracy. We can also test ideas on these models before we even kind of consider making a policy to do X, Y, and Z, right? So we kind of took all of the publicly available data about buildings, and this is mostly coming from tax records, but also the city provided some information. What you see here is a map of building uses that we have mapped in our digital twin. We have looked at kind of the history of building permits within the city of Ithaca, and there we had kind of really a really good data set in the sense kind of that helped us understand how has the building stock changed over time. And you can really see insulation upgrades skyrocketed in a way in the 1980s when the first oil crisis was around. And then we see kind of furnace upgrades in the 2010 era. And then, of course, photovoltaic upgrades are kind of picking up in the kind of towards the end of the graph. And so, of course, taking and synthesizing all of this data has been kind of, I think, the biggest chunk of this work, trying to work with disintegrated data sources that are fragmented across different departments or units. Sometimes it's managed at the city level, sometimes at the county level, and sometimes even at the national labs level where we kind of get information about, let's say, national energy consumption surveys or kind of reference buildings that have been created by the DOE. So we have basically kind of worked hard in the last couple of years to fully automate this data processing pipeline. So our idea was to start with Ithaca, and then of course we would love to scale this to other cities and help them in a similar way. So we take this GIS data, we kind of define these three main tracks here where we try to reconstruct the building geometry. And we use kind of LiDAR data and building footprint data from the city to recreate kind of 3D volumes of the buildings. Then we have a track where we are interested in kind of understanding or mapping, like what are the physical properties of the building? Like what is it made out of? Like are the walls insulated or not insulated? Is it a brick or a timber facade? And then, of course, what's also really important when we talk about energy usage patterns is, of course, how is the building used? Like what function does it serve? How many people are in the building? And what kind of electric appliances might they be running? Computers, dishwashers, you name it, right? And so we are taking information from the DOE there and the national labs that have been surveying the country on energy usage patterns and how they kind of also unfold over time. And then we basically consolidate all of that in what we call an energy model. And energy modeling has been around since the 1980s. Typically, you would do this kind of building by building. In like large architecture projects, you would create an energy model of a building and then look at the energy demand forecasted by that and see if you could kind of optimize that. So what we basically proposed was to take everything we know, fully automate it, and then create around about 5,000 or 6,000 kind of unique building energy models for the city. And that's what kind of drives our digital twin that can talk about building energy. Just to give you a sense, so this is kind of a screenshot from a CAD software that looks at the digital reconstruction. One of the big challenges with digital reconstruction is the workflows that exist out there. They're really designed for very large cities, I would say, where most of the buildings are kind of big boxes. But in Ithaca, that's obviously not the case, right? So here you see kind of on the left-hand side, like a 2.5D reconstruction of buildings in the city, but it doesn't, of course, capture the roof geometries that are very intricate and complex in the city of Ithaca. And so this was one of the big limitations. We wanted to kind of get better at reconstructing the geometry. And on the right-hand side, kind of this colorful plot shows you LiDAR returns from vegetation. The other thing that is often overlooked in kind of energy modeling is actually the impact of vegetation. And if you're dealing with a Walmart with a big parking lot around it, the influence of vegetation is negligible. But in a city like Ithaca, many buildings are kind of under a thick tree cover, and that's what makes this a beautiful place to live. And it adds a lot of quality, it adds shading and so forth. But it's a big headache for energy modelers to account for this correctly. So this is kind of just to give you a sense where the technical challenges were that we try to overcome. And so one example, and this is work done by a team of undergraduate students, Amber, Curtis, Anne, and Tony, who started off with this idea, okay, what if we flew a drone over the city and captured lots of aerial photographs, high resolution photographs, and then we can reconstruct the building geometry very accurately, better than what we would be able to do with kind of available GIS information. And on top of that, we are also interested, of course, in like how are the facades designed? So one of the big kind of data gaps or knowledge gaps were like, how many windows does a building have and how are they oriented? And when we talk about energy consumption in buildings, of course, that's a big and important unknown that we have to somehow solve. And so this team of students used kind of an untextured 3D model. Then they unrolled the texture into a flat image and then basically ran off-the-shelf kind of machine learning methods to segment this kind of image data into pieces. And we were interested in segmenting it in like, what is a facade? What is a roof? What is a window? And you can add to this, like if you train this machine learning model to detect other things like photovoltaic panels on the roof can be detected and sized. Things like HVAC systems, if they're on the roof, we can detect in size. And then that gives us some really kind of meaningful additional information that helps us maybe double check on the permitting data or kind of fill holes in the data sets, like for the windows that we do not have any information. And so we then had like a really detailed kind of 3D model of the city, and we used that to create, first of all, in the first step, we want to understand what's the photovoltaic potential on rooftops in the city. And so these are kind of two kind of buildings taking out of the urban digital twin and kind of showing you kind of a radiation map, like on the building exterior surface, also taking into account some of the vegetation that's around these buildings. And that allowed us to create a map that looks like this, very detailed. It's like a 1 foot by 1 foot kind of a resolution. We can tell you exactly where you can place photovoltaic panels and where you should maybe not place them because of your kind of neighboring buildings overshadowing you or kind of trees that might be casting too much of a shadow on one side or another of the roof. And that allowed us to kind of map kind of the photovoltaic potential within the city. And we kind of try to understand like, okay, so the first question is like, how, if we are talking about becoming net zero, carbon neutral, we need some way of kind of integrating renewable energy production into the kind of design or urban design of the city. And so we looked at different we looked at the potential, if you will, by sector. So we kind of defined 3 scenarios for photovoltaic kind of adoption. One was very kind of conservative, saying only the very best surfaces will use. And then that's the kind of 1,300 kilowatt hours per year benchmarking that you see in yellow. And then the kind of lower end where we said, okay, let's be a little bit more inclusive in a way. Let's also use rooftops that are not that great, but also not terrible, but not like the high performers. So that's kind of the 800 kilowatt hours per year benchmark. And you can see, like, if we are going for this kind of more relaxed scenario or like a mid-tier where we kind of maybe make a compromise between those two, we can see that if we were to really kind of electrify buildings and electrifying all of their thermal load, we are getting close. So if we use kind of all the rooftops, we're actually by sector, we're getting really close to becoming net zero. And that was really encouraging because, of course, Ithaca has other options, right? Like we are not, we do have kind of agricultural land very close by. We have hydropower potentially. and other kind of opportunities to integrate photovoltaics in our urban landscape, thinking of parking lots and other kind of areas that have maybe only a single purpose that could be leveraged in this way. And but it's kind of just the buildings on their own could potentially kind of do a big contribution here. And so we looked at this, but then, of course, and this graph is maybe hard to kind of digest, but let me walk you through it. So here, what we looked at is basically the electricity consumption or with an electrified kind of building, fully electrified building, like the electricity consumption and the photovoltaic potential or the renewable energy potential on site. And we see some buildings basically are have the potential to kind of basically offset their own demand. I wouldn't say they're fully self-sufficient in the sense they still rely on the grid to kind of feed in the electricity at a point in time, and then build like a budget over the course of the year, and then use it when it's needed. So they're not self-sufficient in that sense, but they can basically offset their demand if we are looking at a net metering over a course of a year. But some buildings are basically left out of this, right? So if kind of the renewable energy potential is close to zero or not worth exploring, and for those buildings, I think there has to be some kind of a policy solution. So if we are looking at this net metering as it is implemented in New York State, that's kind of leaving all of the blue buildings out of this, and people in these buildings cannot really benefit in the same way as others could, right? So if you really kind of thinking about net metering, and I'll explain a little bit later why that is really tricky, because we are learning that good investments rely on the fact that you can actually on-site produce your own electricity. And so for those kind of blue buildings in this map, we have to figure something out where maybe they can, I don't know, rent square footage in a solar farm somewhere else, or there's some kind of community solar projects that help balancing out some of these inequitable or unequal kind of access to this resource, right? And so that's one of the models that kind of looks at radiation on rooftops. But also, as we had promised, we wanted to create an energy model for each and every building. So for every building within the city and soon within the county, we have a unique building energy model that we can use to, well, simulate the status quo. That's the one thing, and that's what's shown here. But then we can use these models. They're physics-based simulation models. We can basically play with them and test all kinds of different scenarios. See what how much would it help if we kind of insulated the building more, what would happen, and so forth, right? So, and we can get really high fidelity information from those models. We can get hourly temperature profiles in these buildings. We can get kind of load profiles and so forth from these energy models. But the first thing is to understand how accurate is this really, right? So we wanted to, and what you see in this picture is basically a predicted heating load, and it's mapped out in metric units, kilowatt hours heating demand per square meter of built area. And we can kind of look at all kinds of different things. You could kind of do the same map with cooling. You could do the same map with electricity demand or gas demand or total energy use intensity if you wanted to, or CO2 emissions. Now, the big question was like, how accurate is this? So Avangrid stepped in and they shared really a wonderful data set with us, basically giving us a way to validate our energy consumption predictions at the building level. And what you see here is basically a density plot kind of showing our initial guess, like just using our automated data pipeline. We get a distribution, and it's, if you see, look at the green, for example, that's our initial guess for electricity consumption. And if you look at the yellow color, that's our initial guess for gas consumptions in the buildings. The build energy data is pink. So you do see that the histogram is kind of shifted a little bit, like the density. We're kind of slightly over predicting gas demand in buildings in comparison to what has been measured. And it's similar for electricity. It's not totally off, but it's not perfect either. So we have ways to basically deal with this, where we say, well, some of these input parameters in our physics-based models are uncertain. So we don't, for example, know exactly what is the air leakage rate in buildings. But we do know a feasible range or a range that is plausible, let's say, for these infiltration rates. And so we allow kind of a computer model, an optimization algorithm to take over and try with these models to see if there's a combination of inputs that fits much better the build energy demand. And so we kind of we give it around about 10 uncertain variables within these buildings, and then let it play with them iteratively, if we will, and then optimize the demand so that it kind of really matches closely to what has been kind of reported through metering. And then you can see we can basically get these distributions of energy consumption to match almost perfectly. And this is kind of like the high level summary at the city level. We can kind of zoom into each building within the city and look at these kind of monthly demand curves. And then typically what we compare is really like, do we hit the gas demand in the winter time, in the heating season? And do we hit the gas demand in the summer season for hot water heating, for example? And then do we hit the electricity demand in both of those seasons? So we are kind of like we're not doing really like a monthly calibration, because billing data is a little bit tricky to use in a sense. It's not really telling you exactly in that month this much was used, but it's telling you kind of maybe over the course of the year or the course of the season, like should be fairly accurate. And so if we're looking at the city, I mean, again, this is a simulation model. It's not perfect. It's not like always the 100% spot on. And you see there's this kind of plot shows you simulated and metered gas demand and electricity demand. And you see there's a huge density on the identity line of points. So most of the buildings we can calibrate really, really well. Some of the buildings we can't. And so those are buildings that are maybe worth looking at more closely. There might be something wrong. They might be misclassified in terms of what are they used for. They might be vacant, or something might have gone wrong in the billing data collection as well. So this is also something to keep in mind, that the validation data is not the perfect truth, right? There can be also mistakes in the validation data. But all in all, this shows us that the modeling that we've been doing is, I think, pretty useful in the sense and can be kind of used for kind of scenario testing. So the question is like, what do we want to try out now? What do we want to test? So a lot of the buildings in Ithaca have envelope issues. Their air tightness could be improved. Insulation levels could be improved. And things like thermal bridging could be lowered and so forth. And then we have already heard kind of a lot of these ideas around decarbonization. Often people talk about electrification, and maybe it's helpful to kind of talk just very briefly, like, what do we mean by that? So this is an example. This is from Germany, from Frankfurt, where I'm originally from, a building called that is kind of a net positive energy building. And again, over the course of the year. And so the idea here is really, when we talk about net zero or net positive energy buildings, the idea is to say, well, we have an energy demand. And so typically in design of new buildings, what we do is we shrink that demand down as much as possible. And so you see in the kind of bar graphs on the lower right-hand side of the screen, you see kind of the heating demand. And this is a climate. It's very similar to Ithaca, to kind of just to remind you, heating-dominated climate. The heating demand is very small. The big chunk actually is the domestic kind of auxiliary and household electricity consumption. So this is kind of the appliances, cooking, and these kind of things. That's the biggest chunk left that kind of cannot be optimized much further, like buying Energy Star rated appliances and so forth. That's all already done in this case, right? So the idea is to shrink the load or the demand as much as possible. And you see these are hyper insulated facades with almost like a foot thick of insulation. And then everything that we consume in the end per year is then ideally offset by photovoltaic energy that's produced on site. And this building has facade integrated photovoltaics and rooftop integrated photovoltaics. And then it's offsetting this. As you see, the green bars basically are the photovoltaic yield on the right hand side. So The idea is everything's electrified. We're using a heat pump, a very efficient heat pump system in this case that is actually tapping into the sewer system of the city as a heat source. In Ithaca, most likely we're talking about air source heat pumps because they're cheaper to install. But I mean, maybe there's also potential to look into ground source heat pumps or some other maybe if this is a kind of a larger system and district energy system, then kind of drilling geothermal wells makes a little bit more sense. So we are switching kind of the heating and cooling systems to an electricity-based system, a very efficient system like heat pumps. And then, of course, all the other kind of appliances like dryers that could run on gas or cooking, they're also switched to an electric kind of equivalent. And then we basically want to install renewable energy sources, integrate them in the design of the building, and that's photovoltaics on the roof, and in this case also on the facade. And this building in particular has like an idea of like car sharing with electric vehicles, and also has an additional battery storage kind of in the basement that kind of helps to really kind of actually use the electricity produced on site directly in the building. And this has to do with there's not as like generous the net metering policies like in New York State and Germany. So actually the battery system is necessary to really capture the value of the electricity produced on site in this particular case. Now all that said, so we've defined a couple of kind of very basic scenarios where we said, okay, here's our baseline energy consumption. We're talking about around about 450 gigawatt hours per year in terms of energy consumption in the city. And most of it is heating demand. Then we tested, okay, what if we kind of swapped out all of the gas furnaces, all of the gas hot water heaters, and all of the gas cooking? We swapped that out for an electricity-based system that has a decent efficiency, not the best, but something around the COP of 2.8 or so is what we assumed. And then we can significantly cut down on the kilowatt hours used in the city. And in comparison, we then also did take a look at what if we took all of the building envelopes in the city, and these again hypothetical experiments. So don't worry, we're not coming and installing insulation on your house tomorrow. What would happen to the city if we kind of added insulation that would kind of bring every building envelope up to current code? And that's what you see in scenario 2, showing the envelope. So it does save even more energy than just the electrification, right? And then, of course, we're interested in like combining the two, like what will that do? And then we're interested in comparing kind of the electrification with photovoltaics. That's scenario 4. And then combining the photovoltaics with the kind of full package where we touch the envelope, where we electrify the building, and then install photovoltaics. And again, the photovoltaics are kind of sized to a level where every building is kind of looking out for itself. We're only speccing the system to have a size that meets the building's own demand. So if you remember, that's why we're not getting to net zero here, kind of at the city scale. Like if a neighbor would overproduce electricity for his neighborhood, for example, we could get very close to net zero in this particular case. But if everyone is just sizing their PV equipment to their own demand, then this is, of course, there's a chunk of buildings that don't have photovoltaic potential, and therefore they can't really contribute. And that's why the PV yield does not match the kind of demand in this modeling exercise, right? So it'd be very easy for us to say, well, there's a community, like Ithaca is a big solar community and everyone produces as much as they can and they can then share the credits or sell the credits internally, then this would look very differently. So this is one of those kind of examples where, you know, we hope to collaborate really closely with the city to test some of these ideas, and then if that can be meaningful, maybe that can then be turned into a policy or into a community engaged project where the community kind of leverages some of the data that we can provide to make a decision about how they want to deal with their buildings or their neighborhood. So this is the energy consumption, right? Now, of course, it's interesting. We are all in this for carbon reduction. So we are interested in how much CO2 emissions, and this is CO2 equivalent, not just CO2, it's everything, also the methane related emissions and so forth. So we need to update these labels. Electrification alone is actually very effective, right? So if you're looking at this, the 70% reduction, if we just electrify everything, if we touch the envelope, we are not getting rid of CO2 emissions in the gas appliances, but we significantly lowered the demand. So actually, that's also not so bad. We can kind of cut it down quite significantly. If we do both, we can bring it down a little bit further, even though it looks like it's a little bit less bang for the buck, and we'll talk about money in a second. And then, of course, we have the scenarios where we are comparing with or pairing these measures with photovoltaic production, and then, of course, these are kind of what get us really close to net zero. This idea of net zero being carbon neutral. Now, one of the big questions, of course, with all of this, and one of what we think is one of the big drivers for actual homeowners is cost, right? So we have to develop an understanding of cost when we do this kind of modeling, and that was actually quite challenging to do because there are no good data sources for cost. And we are using a database from NREL, but it is from 2018. So the prices are, I think, outdated. And so all of the modeling and price numbers that you're seeing, take them with a grain of salt. It's probably much more expensive today. But it's helpful to kind of get a sense in terms of order of magnitude maybe, or just kind of back of the envelope, like what are we talking about here and how maybe the comparisons will still hold, not the total numbers, right? So, and like Ithaca currently spends around $30 million on fuel, on energy, kind of operational energy cost in buildings. Now, that's the baseline. If we electrify, now going from a very cheap fuel like gas to a much more expensive fuel like electricity, we are actually going to pay more. And this is assuming that there are no special tariffs for heat pumps and that the electricity prices are kind of like more or less constant, right? And so this is, of course, a bummer because now that's an argument against electrifying, right? And might actually you get some sour reactions from homeowners. Now, if we touch the envelope, we can significantly reduce the cost. And if we kind of pair all of those kind of ideas that we mentioned with renewable energy production on site, we can significantly lower the operational energy costs that we're dealing with. So think about it, like you can go from 30 million as a city to 3 million. That's pretty amazing, right? It's a pretty amazing savings that you can make. But of course, you have to do investments, right? So there's like significant upfront costs for some of these things that we're talking about. So again, we're mapping all of the upfront costs for the scenarios. And of course, the envelope measures hit hard, right? Like they're very expensive. If you think about it, we also included some incentives that we can tap into, even though I don't know the federal incentives, maybe we can cross off the books here. But just to kind of, back then when we did the modeling, they were still there. And so we kind of included them in this analysis. And you can see that, of course, the electrification is quite kind of cost effective. If you think about it, just electrifying saves you carbon. The upfront cost is not that great in comparison to all the other things, but it does come with this higher operational energy cost. So a utility or a municipality could now maybe go in and say, well, maybe we need to have special tariffs for heat pumps so that this kind of operational cost skyrocketing is not happening. So there are policy levers you could maybe play with here. And that's beyond what we want to do, but maybe food for thought. Or maybe these things need to be combined with other measures. So if we are kind of looking at electrification with photovoltaics, we can actually bring down the kind of money we spend on operational energy. So there is a savings, and that's maybe then we can actually have a chance to recoup some of the investments. And the envelope upgrade measures, even though we believe they are really helping us to kind of make the city sustainable and efficient in the long run, they're quite costly. And so just looking at the kind of carbon emissions saved versus the investment costs needed, they seem to be less attractive, right? But think about the thermal comfort issues maybe that are existing in the houses. Think about resilience. Think about peak loads in the grid that may require us to make massive investments in our electricity grid to make this happen. So the question is still, I still have some hope that maybe if we broaden the narrative a little bit and our scope of what we analyze a little bit, that kind of these envelope upgrades can still make some sense in some cases. Now, we modeled kind of return of investment, and you see we took from the literature like what is a good investment. So we heard a lot, 12 years ROI is okay for residential buildings, and 5 years ROI is okay for commercial buildings. And so looking at this then in the histograms, like in the electrification only scenario, basically nothing makes sense from a financial perspective. The minute you do combine these, basically what we're saying is like we have upfront costs, but if we are not saving any money with our operational, then there's no chance we can kind of ever recoup the investment that we made. But if you're looking at scenarios 2, 3, 4, and 5, there are some buildings that actually qualify as really good investments already. Like even with the envelope upgrade, you have a chance to basically recoup the investment costs within the 12 years or within 5 years. So that's quite interesting. That's one way. Now, just one way how you can look at the digital twin. So Hongming did like a whole study on kind of like finding what's the biggest bang for the buck that we can do really per building. So he kind of defined a space with a bunch of solutions, right? Testing all of these things individually, and then looked at this at a benefit cost ratio, so the kilograms per CO2 saved per dollar spent, and then we can map that onto a graph and kind of sort all of the buildings within Ithaca accordingly. And it looks like commercial buildings are the ones that deliver the biggest bang for the buck in the in terms of carbon reduction. The minute we start implementing incentives, though, there's a flock of multifamily residential buildings that is catapulted to the front of this, because there are really good incentives or support mechanisms for low-income multifamily housing projects. And so using this kind of digital twin as a way to maybe kind of find projects that are kind of total no-brainers and you should do immediately and contact the homeowners, versus maybe defining some projects where it will maybe take some convincing to kind of get the homeowners to kind of sign up on these kind of ideas of decarbonization. And so we can kind of pull out, and this is just an example, we can pull out buildings one by one and look at their returns of investments and kind of basically apply a whole range of different upgrades to them. So you don't have to bring the entire envelope up to code. We could just look at insulating the roof or adding some air sealing, what that would do, right? So we can really kind of fine-grain, explore what can be done in the buildings and what would be the benefit and what would be the cost of it. And so one result is kind of a map that shows you where these buildings are that you should maybe be talking to. And I hope Rebecca and Terry are on the call. So take this map and reach out to the homeowners that are in Group A, all the red buildings. Those could be really promising projects according to our model. And so, of course, the big question is like, can we make this accessible, like this digital twin, so that it's not just a research tool? So we invested a lot of time in building a user interface that can be used to kind of explore the data. And this is something that is not public facing at the moment. Only the city sustainability directors and the county sustainability director has access to this. But we would be very thrilled to kind of make that a platform that helps to kind of enable maybe businesses to kind of make use of this, or maybe even homeowners themselves to kind of understand what's going on in the buildings and what could they do and what would they be able to save. We developed a similar thing for the utilities because we wanted to also allow them to understand like what happens when you electrify, what happens to the electricity grid. So we basically can accumulate hourly loads to the grid, feeder lines and substations, and then say, okay, look at the peak winter demand curves, look at the peak summer demand curves, and then basically looking at the hourly data. And if we have time, I can demo this in a second. Future work that we're very interested in, I wanna pick your brain on this. If you have suggestions, is of course like we are interested in looking at ways to make envelope retrofits cheaper. That's research that we want to do in the lab. Looking at serial retrofitting, kind of prefabricating the HVAC system components and the envelope components, and then bringing them to site so that, you know, within 1 or 2 days you can basically upgrade your house without having to leave and creating a huge mess. And so there are some examples from Europe. This is from Nottingham in the UK, where they kind of took a bunch of row house typologies and kind of did these prefabricated kind of upgrades. And so we're really interested in kind of getting some research grant funding to kind of explore what would that mean in Ithaca. We're trying to also collaborate with other digital twinning platform makers and collaborators within the city. So this is a collaboration with KPMG and Augment City and their digital twinning platform, where they have been focusing primarily on flooding, modeling flooding. And so we can combine these data layers in one big kind of digital twin representation to see if there are some overlaps or synergies between these kind of different data layers, in the sense that we can maybe find out which properties are need to work on resilience, which properties are connected. And you see also there's some traffic modeling there. That's another component that we're very interested in as well. So microclimate, heat mitigation in cities, that's another component that we are kind of working on in the lab, creating simulation tools for that. And obviously, we are interested at some point to bring that into the digital twin as a layer, looking at heat stress outside and obviously also inside of buildings. And mobility patterns, another one of those kind of areas where we've developed a software called Urbano.io, which takes, again, publicly available data and can model movement patterns within a city and can show you which streets are busy and where are people when, in which neighborhood. And that allows us to kind of estimate energy consumption and CO2 emissions from vehicular traffic, for example, and then what would happen if you, for example, shifted modes. This is a case study from Los Angeles, where we kind of created like a modeled a neighborhood and densified it, an urban renewal project, and try to make this a more walkable neighborhood. And then the second kind of scenario is looking at adding a transit line, and you can see how this is now activating a really large area in terms of increased walking that's happening either to the transit stations or to that neighborhood. And then we can show how much we believe this would reduce personal vehicle use. And so this is kind of the end of my talk. I do have kind of in the background, if I kind of exit out of this, I have this kind of web viewer. So it's not just a screenshot. This is kind of live, where we can kind of start selecting, let's say, a neighborhood and look at some of these buildings and look at their energy consumption. And then, and then there is kind of the utility kind of lens to it, where we can then flick through some of these scenarios. And if we're looking at, let's say, the winter energy loads hourly, and we kind of flick through the different scenarios, we can see how kind of the capacities of the grid have to change when we start electrifying the thermal loads. All right, and I'll end it here, and hopefully there's lots of questions, suggestions. Thank you so much for having us.
Thanks so much, Timur. That's really a brilliant presentation and astonishing technology. Just amazing. From a selfish point of view, am really interested in the data that you have on commercial buildings, since the flagship program of TCCPI is the establishment and development of the Ithaca 2030 district, which is focused on reducing the carbon footprint of non-residential buildings in the city. Mm-hmm. And I would love to have you come talk with that particular group in perhaps in June at the quarterly meeting that we have, and see what kind of response you get from building owners who are part of the district. But I'm also really interested in the possibility, and we can talk about this outside of the meeting, but the possibility of having a 3D map of the 2030 district rather than just the straight ahead Google map that we have now. That slide that you had right at the beginning was really something in terms of providing an image of the city and what it looks
I'll
like
bring it back up
in
for you.
3D. Yeah, that's
yeah. No, I'd be happy to kind of talk more about this.
yeah, but the vegetation piece is one of the things that most fascinates me. I mean, how accurate is that depiction actually?
Well, I mean, this is now from a LiDAR survey that was done probably in 2020, I think, is where the Tompkins County LiDAR survey was done. So of course the trees have grown a little bit, and
well, that has to be stopped. The data's got to be accurate. So the way to make it accurate is just get the vegetation to stop growing.
Well, so I mean, I think there has to be just kind of regular scanning, right? So, and that's kind of the idea of a digital twin is actually, I think we're kind of like overselling that. What I showed you guys is not really a digital twin yet. I think there has to be a feedback loop, right? So it becomes a digital twin once there is kind of a feedback loop, like a continuous scanning of the city, continuous kind of data inputs from the city, and then seeing how it's operating kind of in a loop. So we are very close to kind of doing this. But of course, the LiDAR surveys are done by USGIS, and so we rely on a lot of kind of these publicly funded or government funded kind of data collection initiatives. But one could kind of imagine that the city does something like that, maybe more regularly, and with a maybe not with an airplane, but with drones or something like that. That's more affordable.
Yeah, I was thinking about the drone piece of this. Do you actually have drones that you own and operate, or do you have to reach out to folks who do and
Oh
hire their
yeah,
services?
so this this kind of project that you've seen here, this capturing that we did here, this is done with consumer drones. They're not expensive. It's like I think a $400 drone
Yeah.
that you can control, and they deliver enough image resolution to do really high fidelity 3D reconstructions of the city. The only thing is you have to kind of have maybe a team that does these flyovers, and then maybe you have to speak with homeowners before you fly over their property with a drone like that.
Yeah, that gets tricky, doesn't it? That church on the left, is that the Episcopal Church on Buffalo?
Yeah, I think so.
Yeah. I drive by that all the time.
This
So
is
like, oh, I know
real
that.
Ithaca buildings shown here.
Yeah, it's really something else. I would like to Rebecca, you're here, aren't you?
I think so.
Yeah, I think so too. I'm always interested in origin stories, so probably a flaw having been trained as an historian, but I really would like to hear the story of how you and Timur crossed paths.
Well, unfortunately, I can't tell you that story. I inherited Timur from Luis very happily.
Well, there's your origin story.
Very happily, but yes, that relationship between the city and the environmental systems lab started before me, and we just happily continued it. So maybe Timur can better answer that question.
Well, I think we are as happy, to continue this relationship, Rebecca. It's been a lot of fun to work with you on this stuff, and I hope we are making a meaningful contribution to your work and make your life a little bit easier, even though sometimes we nag you and make your life harder. But no, I think, yeah. So I mean, it was really kind of coincidence, I think, in this case, that Louise, who was the former sustainability director, reached out. I think he just kind of Googled sustainability buildings, Cornell, and then my faculty profile probably popped up. And but it was coincidence in the sense that we kind of met at the exact right time. So we just had started kind of transferring some of our energy modeling tools to the urban scale, like thinking about urban energy modeling. We're also looking for case studies and like partners, right? So you can do all the modeling you want. If no one listens to the results, then it's kind of pointless, right? So we do really we need kind of the sound chamber of the municipal
Right.
partners to kind of tell us, oh, this is actually an interesting question, or this is what we've been looking at kind of in this initiative, and this community group has been working on this and this. And so that's where we get our inspiration from, right? To do research and to kind of push further.
Yeah. When I was in the provost office at Ithaca College, I was always really interested in finding ways that the research that was being done on campus to connect that to real world problems actually in the community. And I just can't think of a better example than the work you're doing here. It really is remarkable. I want to ask David, he has his hand up, what he's got on his mind, because he's always has something provocative to say.
Great.
Sorry
Hit me with it.
So we've met briefly, Timur, but I don't know. I'm also chair of the sustainability commission, so work closely with Rebecca, and I haven't seen this version of this work in a long time, and I'm incredibly impressed by how much work has gone into it with you and your students. So I don't know if that's provocative, probably not, but I do have one maybe slightly provocative question, and then another one. So the provocative question maybe, but it's really just curiosity, is a lot of the data suggests that on the electrification front, it's significantly cheaper to go with taking the carbon out of the grid at large scale beyond the building scale. So like large solar is twice as inexpensive, counting normal metrics, as let's say doing building scale solar. So that does not account for other things that I think are undervalued, like resilience kinds of issues and the value of distributed generation and microgrids and things like that can sort of have a lot of other benefits. So I'm just kind of wondering how you think in the projections about, if you will, offsite energy production that may be less expensive and still green in relation to this. And then the second question is just if you could say more about, at the county scale in particular, about how you could use this work like they've done in LA to look at sort of future growth scenarios for the population, not just in the city, but sort of beyond the city scale, around issues like sprawl and so on.
Mm-hmm. Yeah, okay. Those are two fantastic questions. Thank you for asking those, David. So again, you're absolutely right, I think, with your first question. Like, this is something that we actually really didn't model, right? So we didn't model the cost to kind of upgrade grid capacity to actually be able to serve all buildings with kind of their new electrified thermal loads, or to meet all of their thermal electrified loads. So there might be, when we say, oh, we just electrify, that's just the homeowner's cost, right? So, but the utilities costs are not part of this calculation, and they probably should be part of it, right? So that we can really make a holistic, we can get a holistic picture of like, where's the money flowing, where are the inefficiencies maybe in the way we're thinking about decarbonizing. And then the whole point of like getting this into kind of this urban scale viewer, if you will, like giving people this kind of bird's eye view on the city, is to be able to identify synergies that you would not be able to see if you went building by building, right? I think that's one of the big innovation potentials of this technology. And I think we're just barely scratching the surface of it, and we're not really making use of this kind of urban scale, neighborhood scale tactics that we could come up with to make the decarbonization a much more cost-effective, much more community-driven kind of project. And so we would be very interested in, making this technology do that, right, or help enable that. So and I think we're not really there yet with this. And so your question is like well taken, point well taken. I think we're still not getting a full picture, complete picture, right? And so Peter is on the call. He's at Avangrid. He's kind of behind all of the data goodness that we've used to validate our building physics models. And I think they're in their grid innovation group, they're doing something like these cost calculations and seeing like how the demand can be met, like the changing demands can be met. So I think it's a matter of like maybe doing a workshop together with them and kind of bringing this all kind of into one system where we can all see it together. The other question about kind of urban development and sprawl is something that we're really excited about kind of exploring further. Rebecca, Terry, and I were just talking yesterday about like how can we, in this digital twin, how can we add a mobility layer here that tells us like if we densified here, if we densified there, like how much can we shift modes, how much can we shorten commutes maybe, where should we invest in electric buses or shuttles and on-demand shuttle systems and so forth. So I think those are really exciting kind of new projects that we would love to work with the city on to kind of get that into the digital twin. And of course, when we talk about load electrification, we're not just talking about buildings, right? So EVs will come and they will also plug in at home, and that's going to be another electric load that the current grid is not handling at the moment. And so having these two things together will maybe make things even more challenging, more interesting, if you will. And so we're really interested in kind of bringing all of these simulation layers together to see it all together, see what if everyone had an electric car and heat pumps, like what would the electric load look like at the building level? That's not part of this version of what I showed today. We're really just looking at building energy consumption for heating, cooling, and operation of the building.
Thanks so much. Really exciting work.
Yeah, Timur, while I was listening to you talk just now, it struck me that you folks are grappling with one of the central issues of our time, which is, oh, this is great. We live in an information age. Look at all this data we have. But what you're grappling with is bringing all those different data sets together in a holistic way that can actually be used in very pragmatic ways.
Yeah, and I mean, we have a lot of data now. We produce even more data, and sometimes it's kind of really like the hard nut to crack is like how to look at the data. And we just looked at kind of two slices of how we can kind of slice and dice the cost question, right? Like, so what are the right metrics to look at? And Rebecca and I talked a bit about this, how should we even kind of do performance benchmarks? Like, should it be energy use intensity normalized by square footage, or should it be energy consumption or carbon emissions by capita, right? Like what is more fair, what is more accurate, right? So these are like really kind of interesting questions that we have a lot of data at our hands, but we need to really kind of think hard about like how do we use it and how do we look at it.
Yeah, really interesting. Dawn.
Yeah, thanks. Peter, I just want to check. We have enough time because I want to make sure Laura gets to go because I know she's got a transportation related comment or question.
Yeah.
Are we good?
Yeah, we're good.
Okay. Thanks, Timur, and your team. Really great, interesting work. I mean, the efficiencies that you bring to understanding the context and energy usage and mapping over time helps to overcome a big hurdle. So I'm a cooperative extension here in Tompkins County. Part of what we do is to take the research at Cornell and bring it out to the community. So one of the things our energy and climate change team does is to work with individual homeowners and building owners in terms of taking advantage of some of the incentives for electrification, for installing air source heat pumps, et cetera. We work particularly with lower income communities, marginalized communities, with our community energy advisors. So it's really interesting because we're very response oriented, but something like your model could actually help us identify where to be more proactive in terms of reaching out. And then another thing we do with our workforce development program is we've been identifying houses, mostly those that, again, apply. So we're more responsive in terms of insulating rim joists. And some of this is also, gathering the data to also see what kind of changes are being made in terms of insulative qualities. Something like what you're doing would make tracking that so much easier and doing maybe even, as you mentioned, more of a community-wide approach or neighborhood approach. So I just wanted to comment that the research for me is really exciting and can be really useful and applied in terms of the work that we're currently doing as far as, the energy transition and looking towards increasing electrification and insulating the building envelopes, et cetera. So thank you very much. No question, just that comment.
Thank you, Dawn. This is a fantastic comment. Thanks for speaking up, and I would love to talk more with you about this to see if we can share the data with you. But we are also very interested in seeing kind of like how you're using the data and kind of maybe finding buildings and then going to these buildings. We'd be thrilled to kind of, I think for us it would be very interesting to see like how spot on was the analysis, and then we do before and after with when you actually engage with the communities. I think that's very, very interesting, and
okay, great.
We'd love to help with that.
Yeah. I have your email, so I'll reach out. Thanks.
Great. Yes, please do send me an email.
That's great. Yeah, thanks, Dawn, for putting that on the table. It's one of the great functions of TCCPI by bringing people together from different sectors in the community to talk about these issues that we have in common, to do the networking. And that was a perfect example of how that can happen. So Laura, I bet you have a question about transportation.
Yes, everybody's right. I was going to dial in with some transportation coming from the Center for Community Transportation. I really appreciate this presentation, and I think the data is fascinating and has so many potentials, as folks have already said. You kind of answered my question initially already, relating to whether there's like a layer in this map that looks at what like level 2 and level private and public chargers are available. So it sounds like this doesn't have that yet, but that's something that I know my group would be especially interested to have a better grip of what is available in our community, as we do have 2 NYSERDA grants that we're connected with actively that are trying to build more EV charging infrastructure locally, and it's just a challenge with the many different steps that are involved. So I think I would love to send you an email and set up a meeting as well to do a little talking shop and strategy. So keep an eye out for that. But yeah, have you all done any sort of initial look into the general layout of charging stations that exist, or expectations, or kind of where is that at all?
Thanks, Laura. And we again, maybe this is something, a longer meeting to have separate from this, but and I'd love to. So please also send me an email and we can set something up. We haven't really kind of looked in depth. Like I think we have some data on the chargers that are kind of within the billing system of the last couple of years, and we do know the location. And we have started setting up a mobility simulation model for Ithaca, but we want to validate this because some of the, I mean, we have the model that I showed there, the tool Urbano, has been validated in Los Angeles and in New York City, and it works really well in these like high density urban environments. We have never tested it in a kind of more rural setting. In particular, because Tompkins County or like Ithaca has like this large catchment area of people coming to the city and then moving out, and so we've been talking with Rebecca to see if we can we set up a project where we can actually do this kind of research to validate this kind of for Tompkins County, and then we could use the simulation platform